Hello, this is Dr. Hasan Abdullah with the course Deep Reinforcement Learning, and we are at the topic Reinforcement Learning, which is topic number 10 in the list of topics which are covered in this course. And the subtopic is E, so this is lecture number 10E. So, this consists of those concepts which are of relatively higher difficulty or complexity, more conceptual. And this video, like other videos, is developed and use the supplemental website, which is a personalized learning management system and accessible at www.easymcq.com/goget. So, what is the future of content delivery? So, the future of content delivery is delivering the content online, and the wonderful features and the benefits are in front of you. And this approach is used by hundreds and tens of millions of users worldwide, which use content delivery for the learning purposes, for education purposes. And we are going to be following the same approach in this course also. So, in green color is the URL for the personalized learning management system, and in blue color are the videos which explain the features of the personalized learning management system with reference to the future of content delivery, which is, as a matter of fact, the present. So what it supports is advanced and basic text search in the content of the course coverage, which is not there in very popular learning management systems. And then, of course, if there are any students with visual disabilities, they can also change the font, the color, the line spacing, etc., to suit them to their requirements, which is also not there in leading learning management systems. And then all the content is kind of opens up and unrolls so as to optimize the small screen of a handheld smart device. And you can also track your progress, what you have covered, what you have to cover. And of course, you can also test yourself online in real time about the knowledge assimilation and the knowledge which you have acquired, and the weaknesses are also identified. So, what is the approach of content delivery? So, there are two approaches. One is the question and answer based, which is proactive, which is engaging, and which is also promotes thinking also. And the other approach is the traditional approach in which a lot of details are provided. So the approach we have adopted is a blend of both approaches, that is Q&A and traditional learning also. So this is the list of topics which are covered in this course, and we are at topic number 10, which is reinforcement learning. So this is the breakdown of the list of subtopics or the concepts which are covered in this video or in this sets or series of videos. So 10A in yellow color are the basic or the fundamental concepts of reinforcement learning. And as we proceed from A to B and so on up to E, the difficulty increases progressively. And for the video lecture 10E, we have the more challenging concepts. And now we move on to the details of the video. So we are at lecture 10E of reinforcement learning. So, how does deep Q networks learn to play games or solve problems? This is a very interesting question. As a matter of fact, for Atari games, deep Q networks have like outplayed the humans also. And this is one diagram, which is a classical diagram by Min et al. 2015. And from their paper, it has been reference cited about 37,000 times. So we have here is an Atari game. This is your joystick, and based upon the images, based upon the game played, so using a convolution neural network and subsequently followed by fully connected networks, okay, they can tell the agent, or they can guide the agent on how to outplay the humans. Okay, so we'll look at the details. So what happens is that in deep Q networks, they learn to solve complex problems. And how it is done? By combining the reinforcement learning principles with deep neural networks. Okay, so that's the guiding thing. So how does it start? The process starts with learning from stored experiences. What are stored experiences? The experiences of playing the game, winning or losing, they are the stored experiences. And those experiences are replayed during the training to stabilize the learning. Now, we covered Q, So central to deep Q networks is the Q value. So what is the Q value? The Q value basically this if you look at the game tree is of exponential size. So it is not computationally viable to calculate the status of the game at each of those nodes in the state space. So we have a Q value which estimates the long-term value of the actions, and that guides the decision making. And that calculation is, of course, not based upon the search space, so it is fairly fast. So what the neural network does is that it approximates these Q values in high dimensional spaces. Okay, and what it leads to, it allows generalization beyond scene states, because if you go to the because if we cannot go to all the states and then label them as the scene states. So what happens is that the training leverages experience replay. What is experience replay? Experience replay is the historical experiences, okay, of playing the game and reusing them, and a target network. And what why to do that? To prevent instability and to ensure convergence. So crucial to DQN, then it is used in reinforcement learning, is the same thing. Balance between exploration of unknown actions and exploitation of learned strategies. What it does that it enables the discovery of optimal policies. So together these components, okay, so together these components form a powerful framework, and that has demonstrated remarkable success in challenging domains like Atari games and beyond. Okay, so they have been very successful. Now, what needs to be taken into consideration is that these deep Q networks, okay, they use deep artificial neural networks to approximate the Q value. Okay, and the neural network, how it is done, the neural network can learn policies, what should be doing from the pixels of the screen and the game score. Okay, and as I said before that it has been shown that DQN surpasses human performance on many of the Atari games. So let's go into some more details. So learning from experience. What is experience replay? Experience replay is using the experience, uh, uh, reusing it. Okay, so this experience replay buffers the store past interaction, and that allows the agent to train on randomly sampled data. So what it does, that any temporal correlations are broken. Okay, so it means that because it's a dynamic environment, so if those temporal correlations are not, if you continue with them, that is not very advisable, because that improves learning. So when you break these relationships, that improves learning and stability. Why, how, and why? By exposing the neural net to diverse examples. And as a consequence, it helps prevent overfitting and ensures better generalization. And what why it is essential and why it is done? Because to master complex environments with several states. So that is what the reality is. Okay, then is the Q values, keeping the score. Now Q values quantify the expected future rewards without actually going and exploring the future of actions in given states. Now what we need to do is update these values iteratively. Using what? Using the observed rewards to predict the future rewards, and these predictions then guide the agent toward more rewarding strategies. Now this is basically kind of a backbone of the improvement policy in DQN. What is DQN? Deep Q networks. And this enables the agent to evaluate the desirability of actions effectively, right? Because you know that space, the solution space is very large. So neural network handling, so the neural network approximates the Q function, okay? And what it achieves, it handles vast state spaces, okay, which are the possible states and which are very large, especially for certain games. Now, this enables generalization to the unseen states based upon what has been seen, what has been predicted. So what is the consequence that makes DQN practical for real world problems? And what is the problem with the real world is that enumerating all states is impossible. It is very computationally intensive and it requires a lot of memory. So with this Q value and with DQN, okay, we transform the raw inputs into actionable knowledge. That is the big advantage. Okay. So training the network. So again, coming back to experience replay and a target network improves training stability. Okay, by decorrelating the temporal decorrelating which we discussed before, decorrelating the samples and providing consistent target value. So what happens that this reduces learning oscillations. Remember that and divergence. We had those learning oscillations in narrow long valleys, which we discussed in gradient optimization. And when these oscillations and divergence are taken care of, that allows the network to converge instead of diverging toward an optimal Q function through iterative updates. All right. And then balancing whenever there is reinforcement learning, there is exploration, there is exploitation, and there is balancing. So now you must it was like should it should be in on like on your fingertips that balancing exploration and exploitation is vital for effective learning. So obviously initially there is more exploration helps discover new strategies while exploitation leverages learned knowledge. So there has to be adaptive policy like which we covered before, like epsilon greedy, and what they do that they ensure the agent continuously improve, okay, and avoid getting stuck in the local optima. Okay, so this I explained earlier. So details are here, right? And this is about the this Q values is a numerical score, right? And this is more explanation, okay, and here are the references also. So we move to the next concept, which is what are stationary and non-stationary processes in reinforcement learning. So uh, let's look at this. So this both are time series data. This is time series data. This is time series data. The range is same. Okay. So what is time series data? That every event has a time stamp and the sequence cannot be changed. So this is called as the stationary time series data because you can see that the average value more or less remains unchanged, right? But over here, that's not the case. That is not the case. So this is regarded as the non-stationary time series or non-stationary data. So so in reinforcement learning, so we have the stationary and non-stationary processes. So a stationary process is the one in which the environment dynamics and transition probabilities and reward distributions and so on, all of this remains fixed over time. So what it allows the reinforcement learning algorithms to converge toward stable policies. Now, on the other hand, we have non-stationary process, and that features evolving dynamics. And since the dynamics are evolving, that makes the previous learned policies obsolete. Why? Because of the shifts in the environment. Now, what we are talking about, the differences, they are not like academic differences, but we have real life, real world systems like robots, traffic systems, and markets which are changing, which exhibit drift or changing behavior. Now, reinforcement learning agents, which are designed for stationary settings, they of course fail in such dynamic environments. Therefore, need to understand the nature of stationary matters deeply. Why? Because it influences whether to use static learning methods or design, okay, adaptive continuing learning systems that detect change and that also allow adjusting the policies, okay, or maintain robustness in evolving conditions. So these are the choices we have to make. So what is meant by stationary in this time series data? Stationary is when a time series statistical properties like mean and variance remain constant over time. That is stationary. Mean and variance remains almost constant over time, which makes it predictable and so you can model it also. Okay, like methods like ARIMA. But non-stationary means non-stationary. These properties change like mean and variance change, and they show trends or seasonality or random walks. So that makes forecasting difficult, and it requires transformations like differencing to achieve stationarity before modeling. Okay, so this is a real life scenario. So let's go into some details. So stationary processes. So these processes assume a fixed transition and rewards dynamics over time. Fixed transitions and reward dynamics over time. Why? Because the environment doesn't change. So reinforcement learning algorithms can consistently learn and refine what the value estimates. Now these stationary processes, they underpin the theoretical guarantees of many classical reinforcement learning methods. Okay, because of several strong simplifying assumptions of the stationary nature. Now, as opposed to the stationary processes, we have non-stationary processes. Now we are considering those environments whose dynamics or rewards evolve over time, change over time. What it means that the optimal policy may shift, which makes the prior learning less valid. So reinforcement learning agents must detect whether they are stationary processes or they are non-stationary processes, or detect the changes and adapt to these changes, which obviously complicates algorithm design. And of course, if they are not properly address these issues, this is going to erode the algorithm performance. Now the next question is why we should consider all of this. Why it matters? It matters because understanding whether the environment is stationary or non-stationary, it guides how robust is the reinforcement learning system, or how robust it must be. Now, as you would have guessed by now, real world systems are often non stationary, they are dynamic. So the agents must incorporate adaptation, and the forgetting mechanisms also, and how to use the prior history. So if you mistook or mistake a non-stationary environment for a stationary one, that is going to cause policy decay, and it is also going to cause system failure also. So if you are interested in more details, so what I have discussed is present over here. Stationary versus non-stationary. A classical board game like chess, okay, or Go, rules never change. But non-stationary system like traffic signals or traffic patterns which are different during the time of the day, or recommendation systems, what you have seen and what you have should be seeing. So they are they're different things. So if you use this chess board playing a game for traffic signal control, is going to be disaster. Okay, so these are the details, and here are the references.